This is our lecture for Pre-Calculus 1.6 about the graphs of functions. So a bit of a review here on some terminology. So we're talking about whether a function is increasing on an interval, decreasing on an interval, or constant on an interval. So let's say your function looks like this, something like this. So your increasing sections of this graph are going to be where you're going uphill from left to right. So you'll be increasing up to here. And then your decreasing is going to be when you're going downhill left to right. And then we be going uphill left to right again here. Now let's say there was a place on this graph where it went flat, leveled off. Okay, so this piece right here is going to be your constant interval, where you're neither going up nor downhill, going left to right. So that's just a bit of a review of terminology. All right, some more vocabulary here. We're going to talk about local and absolute extrema. First, we'll talk about a local maximum. So on this graph here, there are two local maxima. Maxima is the plural of maximum when you're talking about Latin. So maxima is the plural. All right, so here is a local max. And here is a local max. Okay, and these are local maxima because the graph goes up, it peaks out, and then it comes back down, like the top of a hill. And here it goes up, peaks out, and comes back down. So those are local maxima. All right, and now we have a local minimum. So let's take a look at that same graph. So on this graph, we have one local minimum. And the plural would be minima. Okay, so that's the plural. Okay, so we've got one local minimum because the graph here goes down, hits a low spot, a valley, and then goes back up again. So that is what a local minimum would look like. Okay, so in this textbook, when we talk about a maximum or a minimum, we're referring to which many texts will call the absolute maximum or the absolute minimum of the function over the whole entire domain. So let's take a look at our example graph and find out where the absolute local the absolute maximum and the absolute minimum lie. Okay, so I'm looking at this function over its entire domain now. So that's the leftmost point, and that would be the rightmost point. So your domain appears to go, so we're going to read this graph as best we can, from -5 to 3. So continuous over that entire x interval there between -5 and 3. So in there we're looking for the lowest possible point, and that will be your absolute minimum. So this dot right here is your lowest possible point, so that's your absolute minimum. Okay, and now we're looking for the highest point of all, and that would be this point here, and that would be your absolute maximum. So over the entire domain, so absolute over the entire domain. Okay. Okay, now now we're going to take a look at these 14 points here, 14 ideas about the graph we were just looking at. So the first one says find the domain of f. So the domain, and we talked about this a minute ago, -5 all the way to 3. So in interval notation, filled in dot at -5, square bracket, filled in dot at 3, square bracket. So that's how you would write your domain. So the next question says to find the range of f. So if we're talking about the range, we're looking at the y values here. So we're lowest here and we're highest here. So your range is all of this here. So your range then would be square bracket, also -5, lowest y, lowest to highest. Highest y is 4. So that's your range. Okay, so the next question is number 3, list the x-intercepts, if any exist. So we go back and we find the x-intercepts here. I'll just abbreviate it. Let's write them as ordered pairs. So we have one here crossing the x-axis, and that point would be the point 1, 0. And then we have one here, and that would be the point -1, 0. And there's another one here, so that would be the point -4, 0. So notice that the y-coordinate of an x-intercept is always going to be 0. So then next thing, it says find number 4, list the y-intercepts, if any exist. Oops. So y-intercepts, let's see, the places where it intersects the y-axis. So here's a y-intercept right here. So y-intercept as an ordered pair would be the point x is 0, y is -1. So the x-coordinate of a y-intercept is going to be 0. Question 5 says find the zeros of f. Well, the zeros are the same thing as the x-intercept. So x-intercepts and zeros right here are the same thing. It's just another word for x-intercept. They're called zeros because the function is the f of 1. In this case here, let's just try to make this clear. This point right here, f of 1 equals 0. This point here, f of -1 equals 0. And this point here, f of -4 equals 0. Hence the term zeros. Okay, so number 6, it says solve f of x is less than 0. So we want to know the intervals over which that function has a negative y value. Okay, when does it drop below? Where does it drop below the x-axis, in other words? So let's highlight the parts of the graph that are negative, drop below the x-axis. So here and here. All right, so f of x is less than 0 over the interval -5 to 4. Okay, so at 4, it's not, there's not a little line right here. So if there were a little line that said f of x is less than or equal to 0, we would put a square bracket on 4. But since at -4, it's right on 0, it's not actually going to be less than 0, so we would not want to put a square bracket on -4. All right, so then union, All right, let's look at the other piece here. So for the same reason on this piece right here, it has to be less than 0, not equal to 0. Equal to 0 would be at this dot and this dot. So between -1 and 1, we're less than 0. So we're going to use a smooth bracket. Okay, and those are the intervals where our function dips down below the x-axis. All right, so next it says determine f of 2. So let's take a look at the graph and see what the function is what the value of f of 2 is. So that means evaluate the function at x is equal to 2. So when x is equal to 2, our function is valued at 3. So we're going to say f of 2 equals 3. All right, so the next one says solve f of x is equal to -3. So now this time we're given the y value, and we want to find out what the x value is where the y is -3. All right, so let's draw a dotted line through -3 here. Okay, and we can see that it intersects our graph right here. And that looks to be about -4.5. So x is equal to -4.5 is the solution for f of x is equal to -3. Okay, so the next question says find the number of solutions to f of x is equal to 1. So we're trying to find the number of solutions to f of x is equal to 1. So that means we want to find the x values that cause f of x to be 1. So let's draw a horizontal line through f of x is equal to 1. And we'll see how many places it cuts through the graph. So I've got 1 here, 1 here, 1 here, and 1 here. So that means there's 4 solutions, where that means 4 x values, where the value of the function is 1. All right, so we haven't talked about even, odd, or neither quite yet. That's coming later in this presentation, so let's wait on that. Number 9 says list the intervals on which f is increasing. So once again, increasing is uphill. Okay, so let's just write those out again. All right, so increasing, so we're going uphill on this piece of it. So between, so let me just, when we're doing increasing and decreasing intervals, we're always going to use our smooth brackets. Smooth brackets because we're actually talking about what's going on between the endpoints of the interval. So we're going to say -5 to right here, uphill till we get to -3. All right, and then we've got another piece going uphill here. All right, so union, so x is 0 here, and x is 2 here, so between 0 and 2, we're also going uphill. Okay, so number 10 says list the intervals on which f is decreasing. So back to the graph. So let's find decreasing now. So downhill, going left to right. So this is downhill here. and then downhill in this section here. So decreasing intervals. All right, so we've got an interval between -3 and 0, and between 2 and 3. All right, so -3 to 0, 2 to 3. So those are all going to have smooth brackets because we're talking about in between the dots. We never want to be exactly on the dot when we're talking about increasing and decreasing. All right, so the last four, we want local maximum. They didn't do the plural correctly here. It's maxima, local minima, and then the absolute maximum, if any exists, and the absolute minimum, if any exists. So let's look at the graph again. So at the point here, we've got a local max. All right, so that's the value of 4. If you want it as an ordered pair, you would say -3, 4. And then we've got one here. So that's y is equal to 3, or as an ordered pair, 2, 3. Okay, and sometimes the wording would be you have a local maximum of 4 at the x value of -3, or you have a local maximum of 3 at an x value of 2. All right, so then as far as local minimum go, local minima, here's one. So a local minimum occurs at the value is y is equal to -1, occurring at x is equal to 0. So that would be an ordered pair 0, -1. All right, so then the absolute max is the highest point of all, so that would be this point here. So the absolute max is y is equal to 4, occurring at x is equal to 3, so that would be x equal to -3, the point -3, 4, and the absolute minimum would be y is equal to -5, occurring at an x value of -5, so that's the point -5, -5. So this example says, given the function f of x is this rational function, use a graphing calculator to approximate the intervals on which f is increasing and decreasing, and then locate all extrema, approximate all extrema. So extrema is the word that means local or absolute minima or maxima. So we're going to do all those things looking at this graph. So what I've done here is I've plugged it into Desmos graphing calculator, and I've cut and pasted the image into the presentation here. So in Desmos, if you click on what appears to be the highest point on the graph, it'll give you, it's programmed to give you the coordinate pair of that point there. That's either a local max or a local min. So both of these points are programmed into Desmos graphing calculator. It'll give them, usually rounded to the hundred, maybe the thousandths place. All right. So if you're given a function, you're going to type it into the graphing calculator, desmos.com, and touch on your Chromebook what appears to be the absolute max or the absolute min, and it'll supply you with the coordinate pair. Okay, so the absolute max absolute max, let me just abbreviate, occurs at this point here. So y is equal to 4.33 at an x value of 1.732, and this would be the coordinate pair. So it depends on how your question is being asked, whether they just want the y value or whether they want the ordered pair. Just read the question carefully. All right, and then the absolute min then would be this point here. So the absolute min would be y is equal to negative 4.33 at an x value of negative 1.732, and this would be the ordered pair. So be careful that you're inputting it in the homework problem correctly, depending on what they're asking you. Okay, so let's do the increasing and decreasing intervals now. So we're going downhill, all right, to that bottom of the valley there, and then we go uphill to the top of the mountain, and then we go downhill. So you're going to assume that this graph has arrowheads on it here. All right, so increasing uphill, left to right. Okay, so we're talking about an interval. So increasing and decreasing intervals are between intervals, so we're always going to have smooth brackets. So at this point right here, that's this point right here, the x value is negative 1.732. So from that x value, remember increasing and decreasing intervals are asking you for x values. So between here and here, we're increasing. So the x value here is positive 1.732. Okay, so there's one increasing interval. Now let's do the decreasing intervals. All right, so the decreasing, so right here, let's do this one. This is a decreasing interval, so it starts at negative infinity, goes to x of negative 1.732, union, and then we'll do this one over here. This one is decreasing, starting at x is equal to 1.732, all the way to infinity. When we get into calculus, we'll use derivatives to find these local max and min values, but right now we're going to use the graphing calculator. Alright, so here we're asked to sketch a graph of a piecewise function. So we have to look at the domain for each of these pieces here. So this x squared is the graph when you're less than or equal to negative 2. This 3 minus x is the graph if you're between negative 2 and 2. And 4, so a horizontal line is the graph when x is greater than or equal to 2. All right, so let's put that last one in there first. That one's probably the easiest one to draw. So if I'm at 4, when x is greater than 2, greater than or equal to 2, that means I've got a filled in dot, greater than or equal to 2. So it's going to go this way. It's going to stay at 4 for all values of x greater than or equal to 2. So I'll color code it. So this piece is purple. All right, so let's make the middle piece green. So between negative 2 and 2, you've got this line here, y is equal to negative x plus 3. So the slope is down 1 over 1. Okay, so we've got a line there between negative 2 and 2. So let's just figure out what the value of our line is at both of those endpoints. So at negative 2 and 2. So when x is negative 2, if I plug that in, I'll have negative, let's just write it over here, I'll have negative 2 plus 3, so that's 2 plus 3, so that's 5. And then I'll have, when x is positive 2, I'll have negative 2 plus 3, and that's 1. So I've got the point negative 2, 5, and I've got the point 2, 1. Okay, so notice that there's no little line here. So we're going to have an empty circle for these 2 points here. So let's just put those 2 points on there. So I've got negative 2, 5, empty circle. And I've got 2, 1, empty circle. And it's a straight line. We can just go ahead and connect those right there. All right, so we really didn't need to use our knowledge of the slope and the y-intercept to get that in there correctly. But if you look at it, it agrees with the fact that you've got a y-intercept of 3 right here and a slope of down 1 over 1, down 1 over 1. So this is your graph of this middle section right here. So you can get that, if it's a linear piece, you can get it by just plugging in a couple dots. The endpoints are very useful to get in there. All right. And then the top one of f of x is equal to a parabola, an upward facing parabola, if x is less than or equal to negative 2. So let's just take a look at what a couple dots would look like for that one. And we'll do that graph in pink. Okay, so if we're talking about f of x is equal to x squared when x is less than or equal to negative 2, let's just get a couple dots in there. So when x is negative 2, I've got negative 2 squared, so that's 4. Let's do negative 3. When x is negative 3, I've got negative 3 squared, which is 9. So I've got 2 points here. I've got the point negative 2, 4, and I've got the point negative 3, 9. So negative 2, 4. So this is going to fill this dot in right here. And then negative 3, 9. All right, so this is a parabola, so it's going to have a curve to it. All right, so we've graphed our piecewise function. Now notice it is a function. It passes the vertical line test. If you check anywhere along here, at this point right here, it's only got one filled in dot here. So it passes the vertical line test as long as the vertical line goes through once. And it, at this point right here, is still only going through once. So this is a function. It's a piecewise function. So let's revisit the idea of symmetry. So in section 1.2, we learned how to algebraically test for symmetry. And we said that a function is symmetric about the y-axis if you get the same equation when you substitute negative x for x and simplify the equation. And a function is symmetric about the origin if you get the same equation when you substitute negative x for x and negative y for y and simplify the resulting equation. Okay, so we've done that already. Now, when we talk about even and odd classification of functions, a function is said to be odd when it is symmetric about the origin. Okay, so that would be something like a cubic function centered at the origin, or a fifth order, like an x to the third, an x to the fifth, an x to the seventh, something that looked like this. Okay, so those are examples of odd functions. Okay, so a function is said to be even when it is symmetric about the y-axis. So when you're symmetric about the y-axis, you've got something that looks like this, maybe. Okay, so that could be an x squared, y is equal to x squared, or equal to x to the fourth, or x to the sixth, something like that. Or it could have a negative in front of it, which would turn it upside down. Okay, so an even function is symmetric about the y-axis. Okay, so this idea comes in useful when we start graphing polynomials and analyzing polynomials. All right, and we said that a graph that is symmetric about the x-axis is not a function, and we're only talking about functions right now. So what we're going to do now is to determine algebraically if the functions here are either even, odd, or neither. Okay, so we're going to check for symmetry and make a conclusion about even, odd, or neither. So the first function is f of x is equal to 7x. So let's replace f of x with y. So y is equal to 7x. So we're going to check for symmetry about the origin. And if it's symmetric about the origin, then we're going to conclude that the function is odd. Then we're going to check for symmetry to make sure we understand this fully. We're going to do both. We're going to check for symmetry about the y-axis. And if it's symmetric about the y-axis, we're going to conclude that the function is even. And if it's neither of those two, we're going to conclude that it's neither odd nor even. All right, so to check for symmetry about the origin, you replace negative y and negative x. All right, so we're going to say negative y is equal to 7 times negative x, divide by negative 1, y is equal to 7x. Okay, so this is the same as the original equation, so we believe that this function is an odd function. But we're going to check whether it's symmetric about the y-axis. I usually do both to uncover any mistakes that I might have made and also to make sure I understand it completely. All right, so now in order to check whether a function is even, you're going to replace only the x with a negative value. So negative x goes in wherever you have an x. So I have y is equal to 7 times negative x. So y is equal to negative 7x. Okay, because this sign is different than the original equation, it's not going to be even. So it's not an even function. So our conclusion is that this function is an odd function. All right, so here's another one. So we've got the function 3x squared minus 4. So first we're going to check to see if it's odd. Okay, so that would be symmetric about the origin. And the way we check that is we replace both negative x and negative y. And then we're going to check and see if it's even. And the way that we check that is to see if it's symmetric about the y-axis. So in order to check that, you replace x with negative x and simplify. All right, so this is y here. So we've got negative y is equal to 3 times negative x squared minus 4. Negative y is equal to 3x squared minus 4. Divide by negative 1. Y is equal to negative 3x squared plus 4. Okay, so you can see that you've got a sign difference here and here. So this is not going to be an odd function. If we're correct there, let's check whether it's an even function. So that means we're going to leave y just y. We're going to put negative x in for x. So I've got y is equal to 3x squared minus 4. Okay, so the signs are the same. The equation is exactly the same as the one we started out with. So this one agrees. So we're going to conclude that this is an even function. All right, so for this function, this is y. First, we're going to check for origin symmetry. If it's symmetric about the origin, it's an odd function. And the way that we check for origin symmetry is we replace both y and x with their negatives. Then we're going to check for y-axis symmetry. If it's symmetric about the y-axis, it's an even function. The way that we check for y-axis symmetry is to replace x with negative x and simplify. So for origin symmetry, we've got negative y is equal to 2 times negative x cubed minus negative x. Negative y is equal to negative 2x cubed plus x. Now by now, you probably can see that if we divide by negative 1, it basically changes all the signs. So I'll go ahead and do that. Now, these two equations here are the same. So we believe that this is an odd function, but I'm going to check for even, just to make sure I understand this function fully. So I'm going to replace x with, oops, let's fix that, with negative x, and simplify. All right, and check the signs. So this one doesn't agree here, and this one doesn't agree here. So our conclusion is that this is an odd function. Okay, so for this function here, so this is y, we're going to check to see whether this is an odd function. If it's an odd function, that means it's got origin symmetry. Whether it has origin symmetry, the way that we check is replace y and x with their negatives and simplify. And then we're going to check and see if it's an even function, which means it would be symmetric about the y-axis. The way we check for symmetry about the y-axis is replace x with negative x and simplify. All right, so let's do that. All right, so we've got negative y is equal to negative x cubed plus negative x squared plus negative x plus 1. So negative y is equal to negative x cubed plus x squared minus x plus 1. Dividing by a negative changes all of our signs across the whole entire equation. All right, and then we check to see if it agrees. So here's a sign difference here, and here's a sign difference here. So we're going to say it doesn't appear to be an odd function. Okay, so I'm going to check for even. So I'm going to replace x with negative x. And there we go. I'm going to simplify. I'm going to check for sign agreement. So here's a no right there, and here's a no right here. So it's not an even function, so it's neither odd nor even. So my conclusion is neither odd nor even. So the last thing that we're going to talk about is the shape of the parent functions given on the left of the page here. So we want to be able to recognize the basic shape of these without having to resort to using a graphing calculator, and you will be asked to do that. Now, one of the things that you can always do is to just make a basic T-chart. If you ever get into a situation where you can't remember what the basic shape is, just plot a couple points, and that should be able to help you determine what the basic shape is. So a cube root function, the cube root of x function, the first one here. So real quickly, I'm just going to sketch out a T-chart here. So we can take the cube root of a negative number. So I know what the cube root of negative 8 is, negative 2. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is 2. So if I just put these points on here, I can get a pretty good idea of what this guy looks like. Okay, so it sort of looks like a sideways lying cubic function, and they're symmetric about the origin, and you can see that symmetry in the table there. So your basic shape of a cubic function is like a rotated x cube function. So this one's flat. Okay, for the second one, y is equal to 1 over x. You can see that you're not going to have x is equal to 0 as an element in your domain, and we learned that that has a vertical asymptote. So this is kind of a review of something you learned last math course. So we've got a vertical asymptote at x is equal to 0. So let's just take a couple points on either side. You know, let's say we don't remember what this graph looks like. So when x is equal to, let's just say negative 2, I've got a y value of equal to 1 over negative 2. When x is equal to negative 1, I've got 1 over negative 1, so that's just negative 1. So when x is equal to 1, that's 1 over 1. When x is equal to 2, that's 1/2. So you can see some symmetry here. So when x is equal to negative 2, you're here. When x is equal to negative 1, you're here. And what you're going to find out with this graph is that it approaches the vertical asymptote and goes down. It approaches the horizontal asymptote, and the horizontal asymptote is y is equal to 0. Now, horizontal asymptotes we learned by the rules. So the rule was if the degree of the top is less than the degree of the bottom, which it is in this case, your horizontal asymptote is y is equal to 0. Okay, so now on the other side of the vertical asymptote, you've got the point 1, 1 and 2, 1/2. So you're going to approach the horizontal asymptote in this direction and the vertical asymptote in this direction. Okay, so this is the parent function for f of x is equal to 1 over x. All right, now let's look at the parent function for 1 over x squared. So we'll just take a couple points again. We'll go through this exercise here, but you may not need to do it in the future. If you do, though, no problem. All right, so let's say we've got negative 2, negative 1. Okay, 0 is not going to be in the domain again, so we're going to have a vertical asymptote. Let's draw that in. And I have a vertical asymptote. And since the degree of the numerator is less than the degree of the denominator, we're also going to have a horizontal asymptote here at y is equal to 0. So let's put those in first. All right. So then we've got symmetry again, so 1 and 2. Let's do those 4 points just to get an idea. So 1 over negative 2 squared, that's equal to 1/4. And this is 1 over negative 1 squared, so that's 1. So this is 1 over 1 squared, 1 again, and this is 1 over 2 squared. So that's 1/4 again. All right, so let's put those dots on there. So we've got negative 2 1/4. We've got negative 1 1. All right, so this is going to approach your horizontal asymptote and your vertical asymptote like that. And then we've got the same thing going on in the first quadrant. So we've got 1 1 and 2 1/4. My graph is a little tight. So the parent function for 1 over x squared would look like that. All right, so now we've got the function f of x is equal to the absolute value of x. So you probably remember this one. This is one of the ones we study a lot in Algebra 2. So let's just take our standard. We don't have any asymptotes in this problem because it's not a rational function. So the absolute value of negative 2 is 2. So we can see that we're going to have all positive y values. So let me expand my graph a little bit. Let's call this negative 1 and this negative 2. All right. So at negative 2, we're at, this is 1, this is 2. At negative 2, we're at 2. Negative 1, we're at 1. 0, we're at 0. 1 at 1. 2 at 2. So it's the characteristic V-shaped graph. All right, so this is our absolute value function, the parent function of the absolute value function. So then we've got the function f of x is equal to x squared. So just taking a couple values here, negative 2 squaring it, you get 4, negative 1 squaring it, 0 squaring it, 1 squaring it, and 2 squaring it. So we've got symmetry again. So let's just say negative 1, negative 2 again. All right, so I've got negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. So we know this is the standard parabola facing up, centered at the origin, with no translations. So we've studied that one a lot in the past as well. All right, so now we've got f of x is equal to the square root of x. So let's get a couple points. So we need to take the square root. So if x is 4, square root of 4 is 2. If x is 1, the square root of 1 is 1. If x is 0, the square root of 0 is 0. So remember, we're not going to have any negative values for x because then it would be imaginary. So the square root of a negative is imaginary, whatever negative you've got. So those are not in the domain. Not in the domain. So we're not going to have any negative numbers in our domain. Okay, so x is 0, y is 0, x is 1, y is 1, x is 4, y is 2. Okay, so this function would look like this. So that's the parent function of the square root function. So there are no points to the left of this point here. So now we'll do f of x is equal to x cubed. So x, y, let's take a couple points. So negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. All right, so negative 2, 8. All right, so let's say that's here. Negative 1, oops. Negative 2, negative 8. Negative 2, negative 8, that's down here. Negative 1, negative 1. 0, 0. 1, 1. 2, 2, 8. Okay, So we get this characteristic cubic shape that we keep talking about. Symmetric about the origin, so it looks like that. All right, so one more. So we've got the function y is equal to x here. So that's just a line. Okay, so it's a line. Remember, y is equal to mx plus b. We might be able to do this without a t-chart, but we'll do it just for consistency here. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. All right, so that's what we're dealing with here. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. So as you can see, it's just a line with a slope of 1 with a y-intercept of 0. All right, so those are our function families. So you should have enough information now to do the problem set for 1.6. Let me know if you have any questions.